Okay, good morning. Infinite Series Part 5, writing a Taylor polynomial that's centered somewhere other than 0. Okay, this is really, really easy if you know the rule for Taylor polynomials and you know how to write Maclaurens. If you know this rule, that all you're doing is taking your nth derivative times or divided by n factorial and then raising your x to that same power, then this will be really easy because all you have to do is make two adjustments. The first adjustment that you have to make is adjusting where you evaluate your derivative. So in all the ones that we've done so far, since they were centered at 0, we found f of 0 and f prime of 0 and f double prime of 0. Now we're not centering at 0 anymore. So if they want you to center at 2, you're going to find f of 2, f prime of 2, f double prime of 2. If they want you to center at pi, you're going to find f of pi, f prime of pi, f double prime of pi. You see the pattern? Okay, so you will notice in this rule that loves to look more difficult than it needs to be, that all of your f of zeros have become f of a, f prime of a, f triple prime of a. A is where you are centered. That's the center of your polynomial. And remember, it's going to converge there for sure. And that will be the middle of your interval of convergence. The other thing you do, your second adjustment, is like a flashback from Algebra 2, which everybody loves, when you learn to shift functions. So for example, if I said to you that y equals x squared, you know that that's a parabola, that is, its vertex at 0. But if I said to you y is equal to x minus 3 squared, you know that that is a parabola that is shifted over 3. So if you want to shift your Taylor polynomial over, all you do is, instead of having powers of just x, you shift it. So notice, all of your powers of x are no longer just powers of x. They're powers of x minus your center. So if you're centered at 3, all of these quantities are going to be x minus 3's. All that's going to do is take your original polynomial and shift it over 3. If you want to center at -2, then all of those are going to be x plus 2's, because that's going to shift it back 2. Remember, it's always opposite when you're doing a horizontal shift. So those are the two changes you have to make. Evaluate your derivatives at your center. Be careful, it's so easy to just like take them all and evaluate them at 0. Don't do that. And shift your powers of x. Now again, I always just write my shell initially, and so as soon as I see that it's centered not at x, when I write my shell, I do my quantities. But again, we're so used to just writing a power of x that that's easy to forget. And if you forget it, then it's not going to be right. You're not going to get your answer point. So let's do a couple of these. Again, it's not much new other than those two little adjustments. Okay. So here we go. Find the Taylor series generated by f of x near x equals 2. So what they're telling you is this is your center. When they say near x equals 2, or they might say that would approximate values near x equals 2, or they might say that you could use to approximate 2.1. They're saying center it at 2. So if this wasn't at 2, if this was a Maclaurin, we wouldn't be doing much because we know the series for e to the x. This isn't a Maclaurin, so we can't use that. Right. So we do have to take the derivatives of e to the x. But first I'm going to write out my shell. Okay, so my shell for this polynomial is going to look like something over 0 factorial x minus 2 to the 0 plus something over 1 factorial x minus 2 to the 1 plus something over 2 factorial x minus 2 to the 2 plus something over 3 factorial x minus 2 to the 3. I'm going to do one more just because I can fit it. Because I can. Okay. Now notice they said find the series. So as long as I can figure out what the rule is, there's no specific number of terms I have to write. They said write the series, which means our final answer is going to have that summation in it. Okay, so let's take some derivatives, shall we? Okay, this will be fun. All right, so f of x is e to the x. So f prime of x is e to the x. So f double prime of x is, oh, e to the x. All of your derivatives are e to the x. When we evaluate those at 2, all of my derivatives come out to e squared. So all of these numerators are e squareds. That was easy enough. Okay, so let's write our rule. I have every single term, none of them canceled out. They're all positive, so I don't need a -1 to the n. So I'm going to write my summation. I need an e squared. There's an e squared in every single term. Okay. I need an x minus 2 to the n, and I need an n factorial. And I need my first one to be 0. So from n equals 0 to infinity. That's my rule. I don't know if I need to say this, but don't multiply those out. Like, don't FOIL that and try to simplify. No, never. Never. If you do, I will haunt you. Okay, all right. Let's do another one. All right, this time we are writing near 3. So we are centering at 3. So again, as soon as I see that, I'm writing my shell because you know me, I'm going to forget. I'm going to forget to do the -3. Well, nothing if I'm not consistent. Whoop. See how I do that? Okay, so let's take some derivatives. These will be fun derivatives to take. I'm going to switch colors just for fun. Okay, so f of x is 1 over x, also known as x to the -1, don't forget. Okay, so f prime of x, -1 x to the -2, which is -1 over x squared. Okay. F double prime of x is going to be 2x to the -3, also known as 2 over x cubed. And hopefully you're seeing a pattern in your derivatives here. My third derivative is going to be -6x to the -4th. So that'll be -6 over x to the 4th. And I'm going to do one more because I think it will help us find the pattern. Next one's going to be 24x to the -5, which is 24 over x to the 5th. So as you're looking at your derivatives, and again, we're going to evaluate them at 3, but when we have to write the rule. So because we have to write the rule, we want to be able to see the pattern here. I want you to notice they're alternating signs, so plus, minus, and note that pattern. You're going to see it over and over again. It's a factorial, right? 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. When you see that jump from 6 to 24, that's usually a pretty good sign that you've got your factorials there. All right, so we are evaluating all of these at 3. So f of x is going to be 1/3. F prime of x is going to be -1 over 9. -1 over 9. My second derivative is going to be 2 over 3 to the 3rd, so 2 over 27. My third derivative is going to be -6 over x to the 4th, so -6 over 81. And then last but not least, I have 24 over 243 when I evaluate at the center. Okay, so let's see. Again, do not simplify that, because by not simplifying, it's going to help you find the rule. And And that's the ultimate question, right? What's the rule? Okay, so I know I have an x minus 3 to the n, right? Because they're all there. None of them went away. So I'm going to start at 0. I started with an x minus 3 to the n. I also still have my n factorial. So I need to generate these derivatives here. So hopefully, again, we notice we have alternating signs. So I'm going to do my -1 to the n and see if that works for me. When I plug in a 0, that will be -1 to the 0 or 1, which will cause my first term to be positive. That's what I want. Okay. When I plug in a 1, it'll be -1 to the 1, -1, which will cause my second term to be negative. So that's good. All right. I need to generate, though, these fractional numerators. Okay, so I need to generate a 1, then a -1, then a 2, then a negative, or then a 6, then 24. And we just said that's factorials, right? So my numerator of all those fractions is n factorial, right? 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. The denominators of all these fractions appear to be the powers of 3. But be careful here, because if you start with 3 to the n, which is a great place to start, but check it, right? Because if I plug in a 0, that's going to be a 3 to the 0, which is a 1, and that's not what I want. I want my first term, my 0th term needs to have a 3 to the first power. My first term, my number 1 term, has to have a 3 to the second power. My number 2 term has to have a 3 to the third power. So we don't want 3 to the n, we want 3 to the n plus 1. Okay. All right, and again, this generates all the parts. So I know that when you're learning this, it can look overwhelming, like, holy crap, where did that come from? But I want you to notice how I did that, like piece by piece by piece, right? Generate the power portion, generate that numerator, factorial, or that denominator, the factorial. If there's an alternating sign, pop that in. And then worry about generating the rule for where your derivatives came from, right? Your polynomial is always going to have this power part. It's always going to have this factorial part. If you have alternating signs, pop that in. This piece is just your derivatives. Right? So if you can notice as you're taking your derivative, kind of try to look for that pattern, because you're going to end up writing a rule for it. And that's what we did. We noticed that we saw factorials in there. So I kind of knew we're going to see a factorial in this rule. And then we also saw these powers going up by 1, which they ended up being powers of 3 because x is 3. Okay, so hopefully that helps. I'm also posting some practice with these, and there's some like AP type questions where you can try to see how they throw this kind of stuff at you, but it's usually pretty straightforward. They literally say, write the first so many terms of the series for this centered at this. These questions are usually pretty straightforward. All right. Good luck with that, and I will see you soon.